Good evening, everyone. A very warm welcome to all of you on behalf of ISRO Space Tutor KIYE Foundation. This is Shruti, one of the student coordinators from Kalam's Institute of Youth Excellence, and I am honored to be your host for the fourth lecture of S Talks, Science and Technology Talks. In our previous session, we had the privilege of having a lecture with Gnana Gandhi sir, Indian rocket scientist, awardee of Padma Shri. His session was truly engaging, insightful, and received an overwhelming response from participants across the country. Students, educators, and institutions from different parts of India came together with one shared goal to learn and explore. It clearly showed that curiosity for space and technology has no boundaries. And that best part, this journey continues every Saturday. Yes, every single Saturday, we meet to learn, grow, and stay consistent. Because more connection leads to more consistency, and more consistency leads to greater impact. S Talks is not just a lecture series, it is a platform, a community, and a mission. A mission to ignite curiosity, inspire innovation, and shape the future of young minds. Our theme remains Space is the next destination. Let's explore it together. S in S Talks stands for Science and Technology. This initiative is dedicated to inspiring young minds towards space, aerospace, and futuristic technologies. This is a year long online lecture series 52 lectures, 52 speakers, 52 topics, 52 hours of knowledge and inspiration. This is not just a series, it is a movement to build the next generation of scientists and innovators. Through S Talks, you will learn directly from top scientists and industry experts, explore career opportunities in space and defense sectors, build communication and critical thinking skills. As we come to the next thing, now let's take a quick look at a short audiovisual presentation that highlights the vision and achievements of KIYE. May the EV be played. That is a glimpse of KIY, where the dreams of students will get to a direction. Now, I invite one of our dedicated student coordinators, Ms. Hasini, to share her experience with KIY. Hasini, please go ahead.
Good evening, everyone. I am Hasini, a passionate student coordinator of KIYE. I am here to give the feedback of S-Talks. Here, this is where the students are limited to textbooks, but I learned in S-Talks where a new door opened for the science, technology, and innovation through S-Talks. Didn't just gain a knowledge, I gained a curiosity, started asking questions, I started thinking about innovation. I am imagining myself contributing to science and technology. That is the true power of KIYE. And KIYE is a foundation. It's a movement that's shaping young minds, encouraging students to dream bigger and preparing us for the future. Even it is an online, the impact it creates is very real. Brings knowledge to the fingertips, and most importantly, it inspires us to become the better version of ourselves. KIYE is not just teaching students to improve by their knowledge but also change their mindset. KIYE is not teaching them what to learn. KIYE is inspiring them to think and lead the future. So finally, I would like to say, if you want to study, you can choose any platform. But if you want to grow and think innovative, you can choose KIYE. Thank you for giving this opportunity.
Thank you. Thank you, Hasini, for sharing your experience and dedication. It truly reflects the spirit of KIYE. Let's make this session interactive and energetic. You will very soon have the opportunity to interact and ask questions with our speaker. So stay active and stay connected throughout the session. In the meanwhile time, I would request all the people who are here and who are in the YouTube live to like and share the YouTube channel and subscribe the channel for future updates. Now comes the most awaited moment of today's session. It is my honor to introduce our esteemed speaker, Nilang Trivedi sir, scientist G DRDO. It is Sir holds a senior position in DRDO and has made significant contributions in the field of defense technologies. His expertise includes radar systems, missile guidance, and advanced signal processing. With years of dedicated service, Sir has been involved in the development of critical systems that strengthen India's defense capabilities. Sir is one of the advisors of KIYE Foundation. He is also passionate about guiding and inspiring young minds through various lectures and interactions. Today, he will be sharing insights on radar systems, an important domain in modern defense and aerospace applications. We're truly honored to have Sir with us today. So let's wait for a minute for Sir. Until then, I would love to tell my experience and how I got to connect with KIY Foundation. It was 2021 where I was a student, first year student who has aim but don't know where to go. But then I got a chance to come to an event where the biggest scientists of India are coming. And then came the most inspired person of my life, Dr. Somnath sir. In my life, I thought I would never ever see him personally. But then that was the time when KIY Foundation made it real, and I had the time to talk to him personally. That was the power of KIY, and that is the power of KIY. And then I started, I was very curious, what is this KIY Foundation? And I started going to all the events that are happening there. And I understood that it is a platform where students get connected to the top industry leaders and scientists of India and complete their dreams very smoothly. So we request all of you to come to KIY events and explore yourselves. In this meanwhile time, we will go through the classes importance again today. We will be talking about the radar systems today. So Sir holds a senior position in DRDO and has made significant contributions in the field of defense technology. His expertise includes radar systems, missile guidance, and advanced signal processing. With years of dedicated service, he has been involved in the development of critical systems that strengthen India's defense capabilities. Sir is one of the advisors of KIY Foundation. He is also passionate about guiding and inspiring young minds through various lectures and interactions. That's it. Today, he will be sharing insights on radar systems, an important domain in modern defense and aerospace applications. We are truly honored to have you with us today, sir. The virtual screen is yours.
Am I audible enough now?
Yes, sir. Clearly.
Okay. Good evening, everybody. Kindly excuse me for the inconvenience caused. Once again, can you confirm me for the audio?
Your volume has been reduced a little bit than before, sir.
Yeah. Okay. 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 So today we'll be talking about the evolution of radar technology that has taken place since the World War I and II. So as we know, often crisis leads to the necessity or the like you can we have India has experienced recently in the past about 6-7 years back when corona pandemic has struck Asian Pacific countries and as well as the entire world. There were a lot of small or big inventions came out. So the invention radar technology basically were triggered primarily by the events that happened during the World War I and World War II. So if you talk about World War I and II, we all know briefly that there were one side there was Britain, US allies, another side you had Germany, Japan, and allies. Now, battlefield is always like a cat and mouse game, as we know. So one of the requirement of those days was that aircraft was one of the new invention, and there was always a constant threat that if an enemy aircraft is able to penetrate your territory and drop certain weapons, bombs, then how to protect against that. So that very threat gave urgency. It alarmed the scientific community for doing the research and coming up with some solution so as to first detect the aircrafts coming into the your territory. And that was basically first of its kind was very rudimentary approach working on the principle of what do you call sound mirrors. So that was the one of the first approach where sound mirrors were used. The acoustic passive radar systems You can say it was one of its passive early warning system, which was used for amplification and localization of sound waves. Can you see some pictures here? Are you able to see some pictures? Hello? Hello?
Yes, sir.
Yeah, I hope the pictures you are able to see the pictures, images that I'm sharing.
No, sir. Actually, we cannot see your screen sharing.
Oh, 1 minute. 1 minute. What has happened?
Yes, sir.
How about now? Are you able to
Sir,
get the
clearly visible, sir.
visible, right? Okay.
Yes.
So what I was talking about is the one of the first approach for defending the territory, or the very first approach for the devising an early warning system was by means of a sound mirror. The sound mirror concept was working on the very basic physics of the sound wave, where whenever aircraft or helicopter approaches the nearby territory, our territory, let's say hypothetically there are paraboids or ellipsoids used as a means for concentrating the sound wave towards the focal point, and thereby ensuring it gets amplified and the source of the sound gets localized. But this very rudimentary approach had problems because the aircrafts will be coming at a very high speed. Though those days aircrafts had some limitations, so it was partly successful during the very first phase of the world wars. It was somewhat successful, but it was not at all effective as the aircraft technology started increasing. So that called for, and also it was very much susceptible to the background noise. You have to have very quiet place, and it's all again depend on the manual operation, where you have some sensor like a stethoscope, or like you can say microphone kind of sensor, which ends up enabling you to detect the sound. So that limitation led to the invention of something called very first early warning radar system deployed by United Kingdom. Those days, Royal Air Force was like Air Force of the Britain and US and allies. Other side, there was Germany, Japan, and allies. So you had aircrafts like Hurricane and Spitfire on the side of UK and the allies, whereas Germany had Luftwaffe. That's a word for the air force of the Germany. It had a very agile aircrafts. Those days, like during the early 20s, 30s, Germans were leading in the technology of aircrafts actually. So US and UK had a tough time. European countries had a tough time to protect their territory against the invasion of the German aircrafts. Now that was an alarming situation, like do or die. Like I will show you the one map that is very the criticality of that battle is called Battle of Britain, and that has led to one of the pioneering invention in radar. Now these are some of the early warning systems, sound mirrors, which I have discussed with you people briefly. You can see a person is involved
Please
in
excuse
detecting
me, sir.
sound coming from different directions.
So you can just close that tab, sir.
Now, yeah,
Just
yeah.
work on
Now,
that.
next we'll go to next slide. Yeah. Now, this is another example of sound mirrors. that has to be as large as a building. Some of them wish to be as large as building. Chain home radar is the next topic that I want to bring it to you people. See, this is like a chain radar. That means how the name has come up. There is to be a chain of transmitters, tower, all along the coast of the Britain. Now, that was devised as a scheme for detection of the incoming threats. Incoming threats in terms of primarily aircrafts. Aircraft somewhere in the range of 100 to 150 kilometer. The tower height will be typically 350 feet height, or at times it will be around 100-meter height. So this map is shown. So the basically southeast part of the UK was vulnerable by attack from a enemy. That is from basically Germany side. So they came up with a scheme where radar had a set of transmitters. You have a series of chain of transmitter towers, as you can see on the left side of the screen. You also had were accompanied by the receiving towers. So it was basically pulse system where high energy pulses were transmitted somewhere very low frequency UHF band. They were transmitted towards the sky, and they were transmitted in such a way so they were covering a wide area, so that like if aircraft comes from a like you don't know exactly from which direction aircraft is likely to come, so you should be able to search the wide area. So that was ensured by those wider beams. So that was what was ensured. This is the one map which shows a pictorial view which will give you an idea that London was only 20 to 30 meter 30 minute away for if an attack gets initiated by Germany those days. So they had a lot of concern to protect, and they wanted that if the you have to take action towards the incoming threat, you have to have some at least 30-minute time, 20 to 30-minute time for your aircraft to take off. Right. Otherwise, your aircrafts also, if they are kept in some hangars or near airports, they are all vulnerable. Even the all civilians are vulnerable. So to address that threat, they made a grid. As you can see in the map, they made a grid of all transmitter towers all along the border of the UK, almost like 2,000 kilometer. They had ensured this kind of grid or chain, you can say, with which they could come up with by 1939 or 40, they come up with the first ever full deployment of this radar. We can say is one of the first successful early warning systems. Now Germany on the side, otherwise not so much aware of these developments and were slightly undermining this technology, ended up losing lots of aircraft when they tried to invade. So and this ended up like one of the turning point in the World War II around 1940s, where Britain and the Allies were losing side, but this radar technology made them on winning side. Got my point? Like Britain and Allies were on the verge of losing the battle, because of the fierce attacks from the Japan and Germany. So this was one of the technology. Second, like in that, man in loop was always there. So you have a tower, you detect the signal, you get a blip on your display, and the operator uses a goniometer. Goniometer was like an instrument graphic for marking an angle at which approximately the threat is positioned, and then you make a call to the nearby like what you call fighter craft fleets and ask them to take off and take on one-on-one with the incoming threat. So this was one way of man in loop. Somewhere we are closing command control center kind of implementation, which is now fully digitized in a today's era. It is fully digitized, and like it's a network centric warfare, we call it NCW. So, but those days this was the very first, and that also happened to be the very first employment of the woman in the battlefield. That's also in history. Because of the very reason that that particular radar system required the involvement of skilled operators. This is how it looked like. It was like a dipole antenna, HF antenna, strung between two towers, almost 100 meter, and one of them is receiver, and there are two transmitter towers. The pioneer contribution was by Sir Robert Watson and Arnold Wilkins. So we can have more discussion on the latest day, but I'm just trying to give you an overview. These gave a lot of confidence to the scientific community working on the radar, that you can have like some means to protect your territory against the against the threat from the invading aircraft. Next biggest invention of the World War was the proximity sensors. So you might have seen. I hope this screen is visible. Some of you might have watched the movie Pearl Harbor, and these scenes you might have seen. You may be able to recollect. I hope my audio is being received properly at your end.
Yes. Yeah.
Okay. So this is the one of the clip I'm trying to show from the movie Pearl Harbor. The very intent of showing this one is that this was a state of vulnerability. If a fleet of aircraft or swarm of aircraft is uh, trying to attack the particular territory or naval base or air base or civilian setup, unless you have a means to detect it, we are vulnerable. Second thing was that the efficacy of the target. Like even if you are hurling a bomb or dropping a bomb on a territory, but like you would like to have a detonation happening at a precise time and the right over the target. So if you want that, you require a proximity sensing to happen. And for that to happen, there was a need of some sort of sensor which detects reliably and repeatably, accurately the proximity to target. So you might have also seen this particulars, and a gun operator, a soldier, ends up literally manually aiming the aircraft, right? And if he
Yes.
misses the bullet, all bullets will be in vain, right? So that was the one of the need of the proximity sensors. Now proximity sensor looks like this, something like this. This is also one of the biggest invention of the basically Second World War. So where you see an instrument or device which gets integrated in the nose of the those days bombs or rockets. So it had a dual purpose. You may have a target in air, or you may have a target or threat in air. You may have a target or threat on the ground or a sea surface. Either side, it was very difficult that you are able to hit some target in a pinpoint manner, where you are like right on the bullseye. If you are able to hit, then no problem probably. But what if you are not able to hit on bullseye and still you want to inflict considerable damage? Then you have to have proximity sensing, because let's say you are 10-meter away, you are 30-meter away, 50-meter away to the intended target, maybe aircraft. Now hitting an aircraft, as you saw in the last video, right on the bullseye, is like by miracle or by God's grace you can probably hit, but after firing how many bullets you don't know, or how many shells. So if you have a sensor which detects the proximity, you can detonate the warhead and very effectively. And that was another major invention of the Second World War. It had one oscillator, then it had one capacitor to provide the supply, and then it had one antenna. So it was basically working on the directional Doppler ranging system. You transmit an RF signal, you received a Doppler shifted echo signal, you accept the Doppler signal, and by correlating with the projectile's velocity, you can correlate the magnitude of the echo signal with the as well as the frequency of the echo signal in terms of Doppler. You can correlate with the dynamics of the platform, and thereby you can allow the detonation. So this is the kind of thing. See, shell is coming. You on the left hand side top, you can see the two dotted lines are shown. There's a butterfly wings kind of thing. That's basically a pattern of the antenna. It's a donut kind of pattern. Same pattern has been shown in the right side bottom diagram in a elaborative view. So it's like almost in one plane it will be like 55 degree, 60 degree. Other plane is like a 360 degree. So you don't know where is the actually exact target. So by using this was called a VT fuse, variable time fuse or when timer fuse. So one of the fantastic invention which was making unlike pulsed waveform, which was being used by the chain radar, the chain home radar. This was making a CW radar. So this is the way a very first pulsed and CW radar got invented. They were existing, concepts were existing, but in the form of its application to the battlefield, these were the two first applications, pioneering applications, I'll say. that started the tremendous progress. It triggered tremendous progress in further in the radar technology. So this is like all the shells. Now you want to heat a ship, you may heat ship slightly off, but if you have a sensor, you may still able to cause a damage to the ship. That was the concept. Now this is again same thing I'm showing, like you are trying to fire a shell towards the incoming threat, which is seen in this image. Uh, these are taken image for explanation to sharing with you from the some of the archives. So even if you miss the aircraft for hitting it pinpoint, this shell detonation near to the aircraft can still inflict considerable damage or or it can bring it down to the ground. Same thing, like you are trying to spread the efficacy of the blast to a larger area. So you like to blast it at some height, preset height, at some preset height, maybe 100 meter, 50 meter, 10 meter, 5 meter, like that. Now, little away from a battlefield, we will come to some of the radars. Covering all radars is quite difficult. So few radar systems I have selected for giving an overview of the how the development has taken place during the last couple of decades, or last almost 5 decades, 6 decades or so. So aircraft, airport traffic surveillance radar. This is what most of us must have seen actually. Probably you might have seen radar like this. Can you please confirm me for the receipt of proper audio at your end?
Yes, sir.
Okay. So airport surveillance radar, most of us must have seen some sort of some kind of radar which looks like this. It may differ in form factor, place to place. So what is it actually? So it's basically, if you use it for civilian purpose, civilian application like airport surveillance radar, it's basically surveillance radar. So it scans the space by rotating. It is scanning the space all around it in 360 degree. It has a beam width which is of the order of 1 to 2 degree. And even that can be designed case to case basis, but typically is of 2 degree around. It operates around 2.7 gigahertz, 2.9 gigahertz. By scanning the space with such a sharp beam, fine beam, you are able to locate the radar. Incoming aircrafts. Now here is we are talking in terms of the airport surveillance. So basically, air traffic is the goal. You want to give passage permission to certain aircrafts to land, and certain aircrafts you want to allow them to take off. Certain aircrafts you want to tell them that you wait. There is still time for you to land. So these way, for this all decisions to be taken up for by ATC, you have to have radar, which is dependable. So basically, it's divided into three radar systems: primary radar, second radar, and ADS-B. So primary radar basically will detect the aircraft and range to aircraft. Secondary will try to find out whether is like what is there will be transponder kind of system, where whether the which aircraft is it? Is the enemy aircraft, your own aircraft, or if your own aircraft is there, is Indigo aircraft or Boeing or Jet Airways aircraft or Air India aircraft, right? Just in simple words, right? And ADS-B actually is an automatic dependent system, like where the satellite also comes in the picture, and some other extra reinforcement is given in terms by means of the ground stations at various places, so that this is one of the latest introductions, so that your airport surveillance becomes more safety is introduced into it, and you don't have chances of missing the any aircraft any moment. So you are provided. There will be some zones where you may not have a coverage for the for enabling the surveillance. So for those cases, satellites also comes in a picture, and GPS can always provide the lat long and altitude data. So this data, a radar antenna scans the space around, gets the aircraft information, interrogates the aircraft. This info gets displayed on ATC screen, and controller communicates via radio to the all concerned authorities. So this is what you are able to visualize, right? This is one of the very important aircraft. This is one of the very important application of a radar. Now, same surveillance radar, if you can adapt to the defense application. It becomes a battlefield requirement, battlefield application. So principle remains same. Your search, detection, tracking of the signal, that's the electromagnetic signal getting reflected from the target of interest. That principle very much remains same. How you measure the range, how you measure Doppler, how you measure angle of arrival or direction finding, that doesn't change across any application of the radar. But how you adapt to the particular application in the form factor or with the certain parametric constraints given by the application, that differs. Now, another interesting application that is the radar has got migrated, has, we can say, one of the paradigm shift in the radar technology is SAR, synthetic aperture radar. So, any radar primarily gives you three parameters: range, Doppler, and angle, or angle bearing. Angle bearing means like you are looking at an aircraft in the sky. You can have a range to the target, that's how far it is from you. Then you can visualize two angles, one in elevation plane and one in azimuth plane. So if you are scanning, if somebody asks you to scan the space in front of you by looking upward, hey, look at, there is an aircraft. What do? You will try to look up towards the sky and try to rotate your neck as well as the eyeball in the azimuth plane as well as the elevation plane, and at somewhere you will find the aircraft. Now that localization in azimuth plane, elevation plane is the angle finding, right? That's a direction finding basically task. You have a range to the aircraft, there is the range, there's a distance, and you may suppose aircraft is in is having certainly will have some velocity. So the signal that you're transmitting towards the aircraft and which is getting reflected from it will have certain Doppler bearing, certain Doppler. Based on the higher the velocity, higher the Doppler shift, and lower the velocity, lower the Doppler shift. If it's approaching, you have one sign. If it's receding, it will have one sign of Doppler, or another sign of Doppler. Now, apart from these three, how about if you can get an image of the target? Is it possible? Like you get an optical image. So this SAR talks about that. SAR is the concept which is called synthetic. The word synthetic, that means not real. The technique allows for synthetically enhancing the aperture of antenna. Now, I believe like students will be having understanding here that aperture of antenna has, if what you call, beam of the radar, it gets defined by the aperture, and the gain also, right? So larger the aperture, finer the beam, and the finer the resolution you can get in that particular plane. So here the SAR radar gets mounted on a moving platform. The movement of the platform is utilized to an advantage so as to simulate the large antenna in azimuth. Large antenna, if you're using, what will happen? Your beam will be larger antenna, right? So you will be having finer resolution of beam. But you are not having large antenna, you are having a small antenna only. But by synthetically enhancing the aperture, you end up getting a very fantastic resolution in the azimuth plane also. This is again, this enables a day and night imaging. So wide set of applications are possible with this. Here I have shown one pictorial view where you have a satellite-borne SAR radar is there. Now similar thing can be there in any of the reconnaissance or the surveillance radar also, which is mounted on the or integrated on the aircraft, right? So where same principle is that instead of satellite you have now aircraft. You may have probably you can map it to the adaptive to battlefield requirement. You can map it to the requirement of a geomorphical study, oceanography study. Satellite altimetry is one of the major topic for research and exploration, where scientists are keen to explore and find out what is the depth of the certain like seabed or wave heights of the sea, or the wind speed, rate of precipitation, certain types of the rocks and the what you call layers in the crust of the earth. So these all informations, basically if you want to have it, you have to have different types of radar, and imaging radar really helps in a large way for studying the features over the various surfaces. So this is just an operational overview of a SAR radar. ESAT, what do you call CSAT, ESAT. These are all the kind of SAR radars that India was having. SAR, again, you can see here, you can visualize as a grid on the target surface, underneath surface, and grid can be divided into the one plane is the range, another is azimuth direction, and that is how the Doppler. There will be small Doppler shift will be there in every cell. So Doppler beam sharpening is the principle that gets utilized to form the image over here. This is the kind of fine images you get by using SAR radar. Next is the altimeters, radio altimeters. This is also another interesting instrument or sensor which enables the measurement of altitude above the terrain, above the sea surface. That gets integrated widely in aircrafts, UAVs, missiles, helicopters. So I hope my audio is being received properly. I'm
Yes,
reconfirming.
sir.
Yeah.
Yes, sir.
This is one of the GIF file I'm showing, GIF image I'm showing, which shows that aircraft descending to an airport. It is near to the some cliffs and hilly area. Ocean is there. So there are a lot of airports worldwide which has geographical constraints and very thin and restricted airstrips are there. Even though airstrip is comfortable, you require a very precise measurement of altitude while landing so that aircraft safely it comes to the particular airport or it touches the runway. To enable that, you need to have a high accuracy altitude measurement. And for that, early days were making use of the pulse radar because pulse was the very convenient way of transmitting the signal early days. Then it got shifted or shifted to the application frequency modulated continuous wave FMCW radar. Same altimeter systems were being made by FMCW concept. Now next you can see somewhere you will land, somewhere you ocean. You want to have precise measurement of altitude with respect to whatever it is underneath, land or sea. So for which you require a radar. This is the kind of antennas that you find in a Boeing. This is the not Boeing. This is the Airbus. Yeah, this is from the bottom of Airbus 320. You may find a pair of antenna. In fact, while traveling by any one Indigo plane, also, if you have time, 10 minutes, just try and glance. If an opportunity, you will find some antenna on the bottom of the aircraft. During the daylight, you can see easily. Uh, so for the safety purpose, they use redundant systems. So these are C-band systems largely. Mostly they are all working in C-band, around 4.2 gigahertz, and they transmit in the field of view will be around 45 degree with a gain of around 10 dBA. So this again the same concept gets used in Airbus or Boeing or Indigo or Air India like aircrafts. This all gets utilized in the aircrafts, bigger aircrafts, or even you name the aircraft, they will have this system. You name the helicopter, it will have an altimeter. Right? So at suitable locations, you'll be fitting them either in the tail boom of the helicopter or on the fuselage of the helicopter. It will be fitted as I marked it. You can see that some of the typical installations, like how the pattern looks like when it travels. This was one of the major invention which has enabled which has helped the aviation industry a great way. I'm trying to highlight the applications which are related to the our daily life and which have led to paradigm shift in the how the technologies evolve for the aviation's applications around us. So aircraft we know, so air traffic surveillance we talked about, then aircraft landing we talked about. This is the kind of systems it will be. These are the antennas. Systems will be typically like you can say 100 mm by 200 mm by 5 mm 10 mm. This is the kind of form factor. Another one you might have heard of cruise missiles. So you might have heard US missile Tomahawk during the recent conflict with the Iran. The US is having certain number of Tomahawk. So now this missile basically any cruise missile you name that flies by maintaining level on the sea surface. So that also requires some sort of a precise altitude sensor. So that again requires radar. Now these can be either pulsed or FMCW, frequency modulated continuous wave. You can see illuminated swath on the sea surface. So these are all like uh, maybe hypersonic, subsonic, or supersonic. Hypersonic, subsonic, supersonic. Irrespective of that, uh, height measurement is very much inevitable to ensure the uh, attitude of the platform or the missile here we are talking about, which gets maintained at certain height. So why missile has to cruise? First of all, some of may have question. If you are flying at low height, this kind of missiles are used to target and hit the ships. So if you want to hit the ships, you will like to get no, you will not like to get detected. If you're flying at much higher, you are vulnerable by the radars on board ship. You may get detected by radar which are on which are on somewhere in lands also. Some of the islands you may get detected. So if you are flying low level, 5 meter, 2 meter, 10 meter, you are it is very difficult to detect the incoming threat. So that is why that requirement leads to cruise missile, and that cruise missile requirement leads to the uh, uh, development of radio altimeter, precise radio altimeter systems. Harpoon, Caliber, Tomahawk. So these are the certain some of the these are certain applications we discussed. Then we also have one more application called terrain contour matching. So that is something combination of SAR altimeter, you can say, synthetic aperture radar being used as altimeter as well. Or else you can say there is altimeter and there's a digital elevation map pre-stored into the weapon, and weapon will have all the time correlation with respect to the real-time measurement provided by the sensor. You have INS on board, you have GPS on board, you will be doing command filtering or data fusion kind of thing, and the data will be correlated with the pre-stored digital elevation map. So this concept is also called terrain aided navigation, TAN, terrain aided navigation. You have a pre-stored information of some waypoints and the terrain underneath. You want to fly over those waypoints only, and for to enable that, you need to have a precise measurement of altitude above it. So that is called terrain contour matching. It basically is the algorithm that's termed as TERCOM, and the missile which makes use of is called TERCOM missile from US. Next is the early warning radar systems and radar warning receivers fitted in the AWACS kind of platforms or any fighter aircrafts. So you might have heard of AWACS during the Op Sindur operations. Now, when the in today's battlefield electronic warfare scenario, whenever aircraft is flying, it has to have a 360-degree view. Threat can be there from any direction and any moment of time. So the promptness with which it can respond matters a lot. And to enable that, there will be some radars which are on board the aircraft. One of the aircraft radar is the radar warning receiver. So the pilot gets a warning that you are vulnerable from certain threat. Please take necessary maneuveration and the uh, like necessary actions. Arm yourself for releasing a weapon, or go to a safe location, or release a chaff or decoys. So that self defense has to be activated based on the threat that we detect. So for that, radar warning receivers are there. Now a lot of that also has undergone the technological transition from conventional radar systems uh, to the phase aided radar system, where now like people are able to now steer the beam digitally. Digitally, beam is able to steer, like we are able to steer the beam digitally by continuously changing the phase of the signal being fed to the various antenna elements through the TR modules. So that the TR module technology has got significant transition recently, which has enabled phase array systems in a much lower cost, lower form factor. For that, GAN and gas devices available. Basically, this kind of system makes use of a high power. So GAN is the preferred technology, gallium nitride. So TR module with the GAN chips also available, and a lot of research is going in that further also. Then radars you'll find in automotive or automotive applications. You have a lot of advanced cars nowadays. automatic cars are what do you call, they say driverless cars, where you don't have to worry about the uh, like some of the place driver is there. Most of the place in India you see you have a driver in place, but even there are, you may see some videos where totally even autonomous car is there. You you don't have to take any action for reaching from point A to point B, and car will ensure to reach. Then the question arises, how the car will get to know the traffic around it, and how it will put the brake. You keep on applying a combination of clutch, brake, gear. You keep on doing a continuous change in that, right, while driving. Now if someone else has to do it, how it's to do, so you have to have again proximity sensing comes in the picture. So there, like, if you are able to get the relative velocity of the vehicles moving around you, and the proximity also of those vehicle, if you're able to get it with respect to your vehicle, proximity, how far you are from the adjacent vehicle, and what is the relative velocity, then based on that information you can have a automatic cruise control of the vehicle. That is one. So which can give us sometimes alarm. If a man in loop is there, it can give alarm to you, or it may take automatic action without waiting for our actions, because accidents do happen in fraction of seconds, we know. So that can be used for collision avoidance, and car can be subject to sudden brake or the direction change, whatever required. So that way you'll be having a great way, you'll be saving the lives of the people. Now how it looks like, this application, just look at this. Lot of application, lot of cars are nowadays having, even like somewhere cars ranging 20-25 lakh rupees also, like these kind of features are there. Now you can imagine that a sensor, radar sensor, range sensor will be there all along the car, four direction of the car, you will have it. So if, sometimes even you're passing through a tunnel or a overbridge, whether car has adequate margin also or not, that also can be detected. So you basically transmit a signal, you get the reflected signal, you have a delay between the transmitted and received signal, and that delay refers to range. You have a Doppler shift in the echo signal, that refers to the relative velocity. You are in motion, other vehicle is also in motion. So this is another picture which shows you, like you might have seen this kind of systems near airport of Hyderabad. Some of the people might have seen, or Bangalore airport, or any of the highways near, like you may find speed detection systems. So that is also radar system. That is also a dedicated radar system of mounted somewhere on the pole with a look angle towards the direction of the vehicle movement. So we are about to transit to an era where you may find tomorrow, in another decade or so, where every other car, even a normal car coming with a nominal cost, also has a collision avoidance system. So lesser accidents and protection of the people are ensured. So it measures the velocity, it measures the range. So chirps is the name basically given because how the bird chirps. So when bird chirps, or you can basically, that word again comes from the bat actually. When bat, the kind of sound that bat makes has a frequency modulation in it, and from that word comes chirps. Chirps has got another term called frequency modulation, because it's basically frequency modulation. When bird chirp, it happens in the acoustic, what do you call, it's due to sound waves. But when you're dealing with automotive radars and all, you are dealing with a gigahertz frequency. So you have this kind of small antenna. You can think antenna and transceiver systems, LTCC, low temperature co-fired ceramics. Chips are coming in the dimension of 10 mm by 10 mm now. Entire receiver, transmitter, receiver, processor, everything with antenna gets integrated somewhere not more than 2 centimeter, 4 centimeter size substrate. This is just in view how the automotive radar works in the car to avoid the collision. This is the kind of chips. A lot of manufacturers are there worldwide. Texas, Infineon, Renesas are working in this direction. Obstacle detection is also another application. Like say drone is flying, and drone was to avoid that it doesn't get stuck to nearby building or tree. It doesn't get entangled in nearby tree or bushes, or you can say building. Then some obstacle detection has to be done. So for that also, these kind of systems can be used. based on the application, you can adapt it. This is how it looks like. Is a Now industry applications also there. There are certain hazardous chemicals where other sensors are not having much visibility for use. Highly hazardous chemical, or you want to have non-contact type level measurement if you want. Then also in those chemical, basically in chemical industries, you have a use of non-contact radar level measurement sensor. So again, the principle is very same, but the frequency on which it operates, kind of transmit receiver that you design, kind of antenna you design and use, always varies from case to case basis. The cost, form factor, and the constraints of the operational requirements all affect that. This kind of This is like something like 5 centimeter hardware. Entire radar system for short range measurement is available in a 5 centimeter, 55 mm, that is close to 5.5 centimeter. Even in train and metros also, some of the places radars gets used for detection of the velocity. So now this is what we have covered until now. Coming to the one more point, like in a today's world, like last topic we'll take, then we'll close the session and we'll move for the question answers. Waveform selection strategies. Why I'm showing this title or topic? There is a reason. Because today there is an era for electronic warfare. Now we'll slightly jump from civilian application to the battlefield applications, where there is constant threat for jamming and eavesdropping, jamming, spoofing that do exist. If the such kind of threat do exist, then how do you ensure that your radar is not vulnerable to get jammed or overwhelmed by the uh, external noise which is directed towards it? So basically, radar, how it works, it sends a signal which is an RF micro signal towards the target of interest, maybe in air, sea, land. The signal gets reflected. Echo signal is feeble, weak in magnitude, Doppler shifted often, comes back to you. You extract the delay, you extract the Doppler, and at times you also extract the angle of arrival also, if your application demands, and use it for the end application, which can be surveillance, tracking, imaging, altitude measurement, proximity measurement, car auto, right? You name the thing. These are the primary things you do. Now, in this, imagine a situation like what if, like, if a high power jammer is focuses on its power or imparts high energy towards your receiver, then it will be like case you might have seen that if VIP convoy is going on the road, your mobiles will stop functioning for some time, isn't it? Sometimes you might observe that if you are waiting, your roads are blocked and they are reserved for the VIP convoy, and that time mobile will not work. Why? Because that time, for safety purpose, GSM band is being jammed, is blocked. So when you block it, like, basically you're jamming actually. So there is a jammer van which is in the convoy. Often you may see with some antennas. So same thing can happen from an aircraft which is in air, from the ship which is in sea. There can be a big radar on the ground. Now, if you are trying to engage the enemy target, and if enemy like directs a high energy noise, high power noise towards you, how to escape from it? So this calls for concept called to be able to see without being seen. I repeat, to be able to see without being seen. Every radar will like to see and detect the target of interest, but without being seen. You are not seen, that means you have stealth feature. So that stealth also you might have heard in recent operations with Iran and America war. You might have heard the stealth operations, like stealth. Certain aircrafts are stealth, or certain aircrafts are not having stealth features, right? So it's a big subject in itself. We can't discuss at much length, but that calls for a certain features to be added in radar systems. That is one of the advancements. Like these are very, very rudimentary things which I'm telling you. The antenna side lobes should be as low as possible. The beam width, that bandwidth that we transmit, should be as large as possible. The integration time used by radar should be as long as possible. The duty cycle of the waveform should be as large as possible. This all thing leads to eventually using a radar system with the much lesser transmitter power. When you transmit low, you are having lesser chances or lesser vulnerability to get it detected. As if like if I'm whispering, I have lesser chances that somebody will find somebody will be able to listen me properly. But if I'm like I'm talking very loudly, certainly I'm audible to a good distance. People sitting at even some 30 meter also, I can they can listen me, right? So this is a basic funda, that you transmit less power and invite a lesser probability of detection, and use some randomness, frequency agility, code agility, and frequency hopping, noise kind of parameter shifting. So these are a lot of techniques are there. It goes in electronic warfare technology development and design. So where you get radar systems which are called LPA, LPD, low probability intercept, low probability detection. This is the advanced state. Again, there it's like a cat and mouse kind of game. It's like you have a virus, then you have antivirus, and vice versa. So you have it is this that is called ECCM. What are techniques I'm showing you is called ECCM, electronic countermeasure. Whereas if enemy employs something, it is called ECM, electronic countermeasure. So if there is a development in ECM, you have to have counter development. To counter it, you have to have development in ECCM. So it's never-ending race kind of thing, and battlefield continuously keeps on evolving. That's the point I want to convey. So that's the how radar technology is getting paradigm shift with all devices, technology, processing technology. Very fast processor you are getting. Digital signal processing is there now. Devices are available in chip, multiple components, entire transmitter chains. You can distribute chains you can have in a single chip. The cost is reducing for the components, critical components. So packaging is one aspect, processing power is one aspect, antenna feasibility and antenna dimension constraints is another aspect, portability, reliability. So there is like is a multidisciplinary area. If we talk at length, some other time we can talk on the fundamentals of the systems. But this is an overview of the system, how the system has evolved from a Second World War and where we are today. Right. So this is the end from my side for today's presentation. If any questions are there, I'll be happy to take.
Thank you so much, sir. Yes, sir, we are having few questions, sir. Sir, this is a question from the YouTube live chat.
Okay.
Both fighter jets and F1 cars use advanced aerodynamics to stay in control at extreme speeds, but jets want lift, while F1 cars want downforce. Why is it?
No, I didn't get your question. Sorry. Jet, you are saying asking question about the aircraft and the car, right?
Yes, sir. Both fighter
Okay.
jets and F1 cars use
Okay.
advanced aerodynamics to stay in
Okay.
control at extreme speeds, but
Fine. Agreed.
jets want lift and F1 cars want downforce. Why is it?
No, we'll see. There's a that question is not related to really radar actually, but you have a different requirements of the platform. One the platform requires to cruise on the ground, cruise on the road, which is meant for the Formula One race or that kind of speed car racing. You want it that requires a cruising on it, while inviting minimum friction, minimum drag while the driving. Same is the application there, but you require to fly. So for you flight requires a lift, right? The in terms of the forward motion, yeah, both have similar kind of considerations. But again, a car doesn't fly, right? So that's related to aerodynamics. I don't think it has anything to do with the radar systems.
Yes, sir. Sir, could you please stop sharing the screen, sir?
Yeah, sure.
We are having at the bottom.
Yeah, 1 minute.
At the top, we are having stop presenting. Yes, sir. Sir, next question, sir. Sir, in your view, which stage in the evolution of radar technology was the biggest turning point, and why?
Can you repeat, madam, please question?
In your view, which stage in the evolution of radar technology was the biggest turning point, and why?
See, actually, I feel like when somebody is cornered, an individual or a system or a country, it when you respond with the highest promptness and maximum effort, when we are facing the maximum threat or urgency of certain survival level, right? So World War II was that's why I had kept the title. In my understanding, my study says that if you have a like die-hard need for requirement for survival, then you need to come up with that some technology. Otherwise, your existence is under the threat. Now, in that scenario, with that looming threat from Germans and Japanese, Britain could come up with some radar systems. Even Germans also had radar systems. It's not like that we carried everything to Britain, but that phase has led to a lot of radar system development across the Europe countries, across the European countries, US, UK, and European countries, because they already had a background of Faraday, electromagnetic theory, then Marconi's radio, Morse, telegraph, telephony. Those all inventions were already in place, right? Now, but they were never utilized or adapted for realizing a system called radar those days. But that battlefield really demanded that. So I feel like that World War II was the one of the paradigm shifter more than World War One, and that has triggered a lot of interest in radar. And so later, those days, digital equipments were not there, digital processing capability was not there. So rudimentary approach was there for detecting the signal. But later you have now processors, now your FPGAs are there. So you can do a task in milliseconds, microseconds, you can complete a task.
Yes, sir. Another question, sir. So, what are the main practical limitations in achieving real-time SAR imaging, especially in terms of computation and hardware constraints?
Yeah, see SAR, what happens? SAR has got you have a antenna which is required to simulate a operation like a large antenna. Large antenna means like a finer beam. Now, one side I'm saying finer beam, that means larger aperture. Now, if this, it is certainly having limitation for the available time that you have for forming the image. So satellite borne SAR radars will be flying at very high altitude, at least not lesser than lower Earth orbit, right? Or geosynchronous orbit or lower Earth orbit. Whereas any recognized radars also will be flying at good like considerable altitude, like about at least 5 kilometers or 10 to 20 kilometers height minimum. Now, SAR is one of the major challenges that the antenna integrated on the platform has to look down and has to be looking preferably side looking, so has to get you the required illumination of the swath of underneath swath. Swath means I'm saying imaginary area on the terrain or the sea surface that you are trying to project like a beam, invisible beam, like as if like you tied a torch to aircraft and torch is illuminating a beam on the surface, right? So speed of the platform is one of the thing. Second thing is that often like you have a certain zones where your signal will get blank, where how like you have a complex urban in our scenario where beam hits certain roof of the building, and then underneath surface it hits later. So multipath leads to quite a good amount of challenge and clutter rejection. So we call it a clutter rejection. Clutter is something you can define as a something other than the target, or reflections or backscatter from the surfaces which are not of your interest. So those rejections and multipath, speed of the platform, the attitude of the platform at which it is flying. Attitude means like the roll pitch yaw of the aircraft or satellite. That also makes a huge impact. So these are the constraining parameters for that.
Yes, sir. So, we are having another question on SARS itself. Uh,
Yeah, please.
1 minute, sir. I'm sorry. Yes, sir. Can machine learning techniques be used to improve SAR image reconstruction or
Certainly.
target detection?
Certainly, good question. Actually, AI ML has got tremendous potential for its applications in all over the radar applications, not only SAR. Because what radar does basically, radar does the measurement of range only, range, Doppler, angle. Right? These are three parameters only. It does. Any radar system basically is capable of measuring these three parameters, primary parameters: range, Doppler, and the angle, direction of arrival, you can say, right? Now, all radar measurements by principle are of statistical nature. When I say statistical nature, they have a lot of fluctuations because the target towards which we are looking, target surface, if you say like SAR, we are talking about the surface underneath. So then that has got a lot of features on the surface are continuously varying. Like you don't have a flat surface. You are not always going to do imaging on a desert or a plain ocean surface or a flat land, right? You will have a variety of, you have some vegetations will be there, somewhere valleys will be there, somewhere cliff will be there, somewhere some buildings will be there, right? Somewhere you may find that atmospheric attenuation is also considerably happening. So yeah, these are the factors which largely affect. Can you repeat your question a little bit? I think I got slightly digressed while answering.
Yes, sir. Can machine learning techniques be
Yeah,
used?
certainly. So wherever, okay, yeah, got it. So I was trying to tell you that only, that wherever there is a statistical fluctuation of certain parameters, now fluctuations are now that sometimes leads to uncertainty in the measurement, uncertainty in measurement and uncertainty of the certain features while forming an image. So certainly there is a lot of scope of AML and image processing, image formation, and mainly image processing. So there's a lot of tremendous scope will be there. So you can have like variety of cases if you take up, like every application itself is like its own field of challenges. Like if you say, how to say, geomorphological studies, if you say, that means the study of the features on the earth surface, like where the geological scientists will be working on, right? Or you want to make the study on the uh, certain features of the satellite, seabed, bed of the sea, or the sea wave heights. Now sea wave heights, a lot of fluctuations, right? You want to come to some optimum numbers, you want to have decide the rate of precipitation, wind speed. A lot of applications are there where arriving to right numbers, parametric measurements will be very challenging. So AI can certainly help you. Certainly help you.
Yes, sir. Can we take one more question, sir?
Please, please.
Yes, sir. Uh, what are the different types of radar systems and how are they classified based on their function, applications, and frequency ranges?
Primarily, that is why I started with the presentation of the two types of radars. One is the pulsed, and one is the continuous wave. Right. So if you have like patience, I can show you one slide. Probably that makes a little. Shall I show you one slide so that makes an easy understanding?
Yes, sir.
Okay. Are you able to see my screen?
Yes, sir.
Okay, just I'll go through two three slides that will help you. In thought, I thought of showing it to you. One of the signal called FM signal is also called signal because like it simulates, it mimics the basically frequency in transmitted.
Sir, we cannot hear you, sir, properly. Yeah.
Are you able to get me? Are you able to get my voice?
Yes, sir. Now.
Yeah, okay, fine. See, the when bird chirps, you have a quieter sound or louder sound, two way you can classify. Other way you can classify with the lower pitch and higher pitch, isn't it? Right? Right.
Yes.
That's the pitch is the sound, is the frequency, and the quieter and louder when you say it's about the amplitude. So there is a kind of modulation I'm highlighting over here. Second case is having a frequency modulation. First case is having a amplitude modulation. Let's go next. I'll show you something like probably can you measure. Yeah, this this was my point actually. I wanted to ask this question and it was it. Are you able to see this slide?
Yes, sir, clearly.
So my question, again a reverse question I'm asking to explain you. Can we measure range if we are able, if we are just transmitting a sine wave kind of signal? Can we measure range to the target surface or target? Let it be any kind of radar with a simply by sine wave, a cos 2 pi ft, a cos sine 2 pi ft. No. Answer comes no. So that is where the one particular classification comes based on the type of waveform that we are using. Then why no? Because there is no marking here where the waveform is starting, right? You have a continuous wave. Now, even if you get a x of t minus tau, a delayed replica of the sine wave, you may not able to exactly correlate with the instant of the start. Now here, instead, if you do a modulation like this, the same sine wave has been interrupted now by the switching action. So you made a 1 microsecond pulse and some repetition time is there. Now with this, you can measure the range. The first waveform, what was there, with which you can measure Doppler. Only Doppler you can measure. Because you can have suppose you are transmitting a 1 gigahertz waveform, your 1 gigahertz will come back with some Doppler shift. 1 gigahertz plus some kilohertz Doppler shift will come back to you. The kilohertz Doppler, if you can extract, it talks about the Doppler, relative velocity. So you can get relative velocity with the continuous wave radar. Whereas with the pulse radar, you can get a range at first and then you can get Doppler also. Then with FMCW, which I was talking about earlier, I'll show you that one. Like again, it will diverge. It will make us diverging the topic. But if you talk about FMCW radar, that this kind of radars, which is going from low to high frequency left side and high to low frequency, that will enable again range and Doppler both. So basically, primary classification will be based on the waveform that we use: pulsed CW, frequency modulated CW, or a phase coded CW, or a pulsed LFM, or a phase coded pulsed waveform. Again, in the phase coding also, there are different types of waveform. Different random codes are there: polytime, polyphase, Parker codes are there. So based on type of waveform, you have one classification. Based on the platform on which it is gets used, like a ship-based radar, ship-based on in ocean, land-based, the ground-based, satellite-borne, aircraft-borne, or you can say a one particular category, missile-borne or airborne radar. So this is another classification. Third classification will be there based on the number of antennas used. Some of the radars operates with only one antenna, and some of the radars requires 2 antennas to operate, or even MIMO radars also there. So like based on antenna configuration also, it can have a type, right? Then another radar application can change based on the this antenna configuration. Again, I can say like is a phase radar system, like digital beam steering system is there. So based on that also, you can have a one classification of the radar system. Further imaging, further you can have a classification by application, like surveillance is one, tracking is one, surveillance, tracking, reconnaissance, imaging, ranging. These are all the primarily different types of radar systems. Basic fundamental remains same, but this way you can classify.
Yes,
I hope I made your point.
yes, sir. Sir, uh, with your permission, can we take the last question, sir?
Yeah, please.
Yes, sir. We are having Sneha in the meeting, sir. She wants to ask the question. Ms. Sneha, please go ahead.
Hi, sir. I'm Sneha.
Yeah, hello, Sneha.
So, thanks for sharing the valuable knowledge, sir. So, I would like to know which area of the radar systems need to be improved the most as per India's point of view. And nowadays, systems are becoming digital. Do this radar system also become fully software controlled?
Yes, good question. Very good question. I appreciate your thought process is triggering you to ask this question. Really appreciable. See, radar as a system is comprising of major. What are the building blocks that you think? One building block is what? Antenna. You require an antenna to transmit and receive signal, right? To transmit and receive, you require some antenna. maybe any type, patch, waveguide, squinted beam, or phasor antenna, linearly polarized or circularly polarized. Name the antenna, but there is some antenna, right? So antenna technology is involved. Then to transmit the signal, the transmitter side, what is required? Main component is the waveform generation. You have to generate a waveform at certain frequency, then you have to amplify and transmit, right? So at certain frequencies, the amplification becomes challenging. At some high frequencies, if I go to like carbon and above, the amplification process is not that simple. You have to have devices. You have to have devices for that, right? So that is amplification, and that too specifically, if you want to transmit a high power signal, it becomes even further challenging, right? So that power generation, signal, RF signal generation or micro signal generation with the required power level is one of the basic challenge. Other one I told you about the what you call processing also is one of the challenge. But processing nowadays largely you are able to manage with the available FPGAs and processors. But if you talk about a country like us, we certainly need to come up with our own processors and set of processors and FPGAs where we ourselves have the tools to program it instead of depending on analog devices, Texas or Xilinx, Actel, right? So you are self-sufficient. You should, because transmitter is one, the receiver side also is critical components are we having like low noise amplifiers, mixers and all. So these components again, in the day one you cannot make all these components. You have to have like a forbidden learning curve, and industry of the country has to get matured in that directions. So for if you want to have everything with you, primarily you have to have components with you, the building blocks, right? Components you should have, and to have the components we need to have the chip manufacturing, for which I believe that present government has taken a lot of initiatives. So a lot of VLSI specific impetus is being given to the industries. You have to have chip. Your chip may not be as fancy as Xilinx or Altera, or but it should do a job for you, and that should make you self-reliant, right? So that is the one direction. Third direction, we have to look into, like, once you're cheap and all, you can always do the programming. So doing programming and developing application, that is not the limitation. Basically hardware where the physics is involved, so that is the most challenge. Making compact things, right? Those are the kind of challenges.
Thank you, sir. Thank you so much.
Yeah, yes. Thank you, Sneha. I hope like I have answered, and hope you could receive the message that I was trying to convey.
Yes, sir. Thank you, sir, for answering the questions and encouraging our young minds. And thanks to all the participants for your active involvement.
Kindly excuse me for the initial hiccups in connecting with for the session.
It is fine, sir. We are having you. That is the blessings that we are having.
Thank you. Hope your audio was clear. I think the remaining part of the, except the initial hiccups, audio was clear, I believe.
Yes, sir. You
Okay.
were super clear.
Okay,
Yes.
okay, Shaharsha.
Yes, sir. As we come to the end of this session, I invite Ms. Saharsha to deliver the vote of thanks. Saharsha, over to you.
Thank you, Ms. Shruti, for this wonderful opportunity to deliver the vote of thanks. Respected dignitaries, teachers, students, and my dear friends, a very good evening to everyone present here. Myself, Saharsha, and I feel extremely honored to stand before you today to deliver the vote of thanks on behalf of KIYE Foundation, along with the entire organizing team of the STOCKS lecture series. First and foremost, I would like to express our heartfelt gratitude to Shri Nilang Trivedi for his valuable presence and inspiring works. Sir, your insights about space, science, and technology have truly motivated all of us. Your journey and achievements are a great source of inspiration for students like us. Sir, your words have truly ignited scientific curiosity among our students and encouraged many to dream in the field of science and technologies. We are deeply grateful for your time and effort in sharing your knowledge and experiences. Your journey and achievements have encouraged us to dream big and aim high. I extend my sincere thanks to our organizers for arranging this wonderful session. Special thanks to our teachers and coordinators for their continuous support and guidance. I also thank all the participants for their active involvement and enthusiasm. Your presence made this event more meaningful and successful.
We are thankful to everyone who worked behind the scenes to make this program a grand success. Once again, thank you, Shri Nilang Trivedi sir, for inspiring young minds like us. We hope to carry forward your words and contribute to the field of science and technology. This session has been a powerful reminder that space is the next destination and we must explore it together. Before I conclude, I warmly invite everyone to stay connected with us for upcoming initiatives. Join our WhatsApp channel, subscribe to our YouTube channel, follow us on Instagram, visit our official website. Let us carry forward the legacy of Dr. APJ Abdul Kalam by nourishing scientific temper, encouraging innovation, building a knowledge driven future. Thank you once again. Jai Hind.
Thank you, Jain. Thank you. Thank you.
Thank you so much for your gratitude words, Saharsha. We would also be very happy if we have many more lectures like this in the future, sir, like minimum of 2 at least. And as said by Saharsha, let us stay connected, stay curious, and keep
Yeah,
learning.
get connected with me if you want to have something on the fundamentals. This kind of talks are slightly difficult to fit into the required time here, because when you talk about a wide spectrum of applications, you can just track the abstract part of it. Like fundamentals are very essential. Fundamental part is very essential. So sometime if you want to have on that, just connect with me. We can have an exclusive session on the essentials of the radar system design.
Thank you so much, sir, for this opportunity. We will keep
Thank
this
you.
in our mind.
Thank you all.
Yes, sir. So as we come to the end of the session, let's end the session. Stay connected, stay curious, and keep learning, because truly space is the next destination. Let's explore it together. Have a wonderful evening. Jai Hind. Thank you so much, sir. Thank you, participants.